Hi everybody, my name is Katz and we're going to talk to you today about JavaScript Obfuscation. It's all about the packers. But before starting, let me introduce myself briefly. I'm a former OSP Israel chapter lead. I'm data-driven security researcher, which means I work a lot with data and data drive a lot of my research. I work today in Akamai. When I try to define my role in general, I'm trying to say that, hey, I'm trying to move security challenges into the science and solution space. And hopefully the story that I will tell here today and the research that I will show here today actually will make more sense explaining this sentence. And last and definitely least, I have a really boring social network persona. Therefore, I don't encourage any of you to follow me on Twitter on _Katz. Boring. Don't do that. Okay? Let's get started. So how did I end up here, right? I think that's the beginning of some of my presentation in that sense. Because when I try to ask myself, how did I end up here? I think it started over a year ago when I was doing some research about JavaScript Obfuscation. And during that research project, I was, the outcome was 3 different blog posts. One is talking about different techniques being used by a variety of JavaScript obfuscations and obfuscators. The second one more around the trend that we are seeing of those kind of files being used in the wild. And the third one, which will represent the image that you see in front of you, was taking one very simple yet, obfuscated JavaScript code, the one that could get into a snapshot, and try to break it up to small pieces and try to better understand what really happened in those kind of files and the obfuscation techniques and the way the flow works in those kind of files. And while I was doing that, I asked myself a question, well, that's a nice thing, right? Doing that kind of obfuscation for a given file, but I want to do something else. I want to do that on a much larger scale, do that on a much more files than a single file. And it's really, it's really challenging doing that file by file. So I asked myself, and I asked myself, can I start a new research project that will lead me to have the ability to do the following thing? These are the objectives that I had in mind. The first one was, okay, I need to build up mechanism, a tool that will enable me to do detection of JavaScript being obfuscated. More to that, it would be really nice if I would be able to tell that JavaScript is being malicious. The second objective that I had in mind that I need to do that at scale, right? As I mentioned, it's not a matter of files or few files. I need to do a lot of files and scan them and be able to make a decision based on those files. And those files could be benign files or malicious files or obfuscated or not obfuscated. I need to make a decision based on those files. The third objective was to use static code analysis. Well, and in that sense, it's very related to objective number 2. Because I was into working in scale because I wanted to scan a lot of files and because I needed to have really good performance, my assumption was that I'm doing static code analysis for any given file that is given to me, right? I'm not doing rendering for the file. I'm not running the file as if it was inside of a browser. I look into the code being sent from the server to the client, look at that file and make decision based on that. So that's a really important assumption here. The third objective for me was the Pareto principle. And that means, in the context of this research, is that, well, when we look into a research project, we need to say what are the goals that we have. In my case, what are the detection goals? And my assumption is that I'm trying to do 80% of all those samples that I can see in the wild that are being obfuscated, and I assume that those 80% of those files that are being obfuscated in the wild are being the result or the outcome of 20% of the packers that we see out there, right? When I mention packers in the context of JavaScript, I mean a software that will take a JavaScript code, regardless if it's benign or malicious code, and will do the obfuscation process of that code, creating a different file that looks different from the original source code, and it's being obfuscated. That's the main purpose of the obfuscation. Take a given context and a given code and do some sort of a manipulation and some sort of a tampering for that code to do the same functionality but look very different. Okay, so in the context of those things, I have 3 blogs. These are the 3 links for the 3 blogs that I mentioned at the beginning of 1 year ago. Now, okay, so we have objective. Here comes some of the question, the research question that I had in mind. The first one was why and how JavaScript is being obfuscated, and we'll try to address that. The second one was what are the number behind JavaScript obfuscation being used in the wild? What we are seeing out there? Whether that's really trendy kind of phenomena, is it more niche kind of things that we are seeing out there? We will try to answer that. Is it possible to detect obfuscated JavaScript, right? That's the main goal here. I need to be able to look into a file, make a decision if that file is being obfuscated or not, based, again, the Pareto principle. We want to not be able to detect all cases of obfuscation, not all proprietary obfuscation out there, but the most common and the most frequent obfuscation, JavaScript obfuscation that we can see out there. And the last item in the question was, will I be able to create, an ability in that sense to differentiate between a file that I know that it's being obfuscated and whether that file is malicious or not. I will need to address that question. It's a very important question, and we'll try to see if we will have some sort of a technique or a high-level concept to do that thing. Okay, so let's start with the first question, which is why JavaScript is being obfuscated. And in that sense, to answer that, we need to address, the meaning of JavaScript. JavaScript is actually source code that in most cases we run on our browser, meaning the code actually exists on our browser, therefore we can understand the logic and the things that the code is executing, right? And once that's really simple in that sense, here come the reason why some of those codes are being obfuscated and making them hard to be read, right? If I want my code, my JavaScript code, not to be easily understood, I will write it very, in a ways that will be hard to read that code and understand the meaning of that code. And more to that, I might add some, traps to make that debugging of that code even harder, right? These are the objective reasons, and you can do that for a benign reason, like a normal file, or you can do that if you have malicious intent in mind. And in that context, the second item of trying to answer why JavaScript is being obfuscated, in the context of adversary, where we know that from a defensive point of view, there's a lot of solutions out there that are using text-based or hash-based detection to flag a malicious file being used in the wild. Doing obfuscation using JavaScript will create different variation of the same code or same malicious code being used, and as a result of that will lower detection rates, right? And in order to elaborate more on that and my concept of why JavaScript is being obfuscated, I'll try to look into that from an adversary point of view, right? So again, adversary, but before adversary, let's look on the defensive point of view. Once you have more resources, right? More resources are required from you, and more time is required from you in order to detect a given file of being malicious. That will end up with lower detection rates. That's the equation that I have in mind, right? Whether you agree with that or not, it's a matter of a concept, right? When we try to think why threat actors, why cybercriminals are introducing new and more advanced techniques to try not to be detected, in our case, JavaScript obfuscation, right? They are trying to create more challenges for us to have more resources and more time. And at the end of the day, that in most cases might lead to less detection rates. And from an adversary point of view, that's obviously create higher success rates or more revenue or more money off their scam, right? That's the equation that I had in mind for us to better understand why JavaScript is being introduced in the wild for an adversary purposes. Now we answered the why. Let's talk about the how, right? How JavaScript being obfuscated. There are three major, let's say, bullets in that context. First of all, once you create a code that is, repetitive in a sense and meaningless, and do that for function and variable name inside of that code, trying to look into that code, try to understand that code, make it much more harder. It's not readable in that sense. More to that, if you're using anti-debugging code techniques to make sure that if someone tries to understand what your obfuscated code is doing, at the end of the day, it will be harder for you to do debugging for that and better understand, because someone was putting some traps and creating some more challenges once you try to debug that. It's not impossible, but it makes it much more harder, taking much more time, much more resources, right? And the third item here is that once you're using consumption of resources and time, for example, introducing dead code into your JavaScript code or using timers inside of your code, that's also create much more challenging kind of detection, because again, it will take more time, because running on dead code and running with timers takes more time, and it might take more resources because you need to consider the time and the effort that need to be done. And these are the main, well, let's call them main buckets being used for creating obfuscated JavaScript code. So, right, the name of the presentation is all about the packers, and some of the way that led me into that research, and that's some of the examples that I was able to see over a year ago. And I look on 4 different samples of code, and those 4 samples of code, they're not the entire code, they're a snapshot from a given code that I was looking into. 3 different files, right? Definitely different files, and the reason for that, because they represent different threats. The 2 upper ones are phishing webs or phishing pages, and the 2 lower ones, one is Magecart and one is malware dropper. And in that sense, they were different, right? But I think they were the same, right? Once looking into them, and I'm looking into them now, they are not the same, right? Like high-level view on that, it's not the same. But if you do some sort of try to obfuscate or abstract some of the things that we're seeing out there, we can see actually some sort of a template here, right? And the template is it's the same functionality. It's the same function being used with different variables name, different values, and etc. But what you are seeing is an anonymous function with 2 variables that has inside of that function a variable that contains a function, right? And that function is doing a while with a decreasing on an integer, and then doing some pushing and shifting, meaning doing some manipulation on a given payload given to that function, right? And that pattern happens on all those 4 examples, right? They are different, but they are actually the same. And that pattern actually represents some of the packer functionality being executed on a given file to create some sort of a obfuscation of that file, right? So now comes the question, how can we move this concept, right? Once we have the understanding that we have some sort of a pattern or a template, moving that into the space of being able to have better detection. And this is what I was doing. The concept I was saying, hey, let's take that given, well, let's say any given source code, JavaScript source code that I have, create a representation of that source code in an abstract syntax tree, which is AST. It's a representation in JavaScript, it's a JSON-alike representation of each or any given JavaScript file that is given to that sort of a parser. And once you have that in mind, then you can start to say, hey, well, I'm not looking for the exact code that was executed. I'm looking for the pattern that was executed. In our case, right, the pattern was some anonymous function and some while statement and some pushing and shifting for a list inside of that JavaScript. And these are the parts on that AST that I'm looking for. So if I will run on a given AST, right, and look for those kind of patterns, then I will be able to say, hey, I can see that functionality being executed without going into the details of the name of the variables or the name of the function and stuff like that. So that was the proof of concept that I had in mind, and I built a proof of concept of that. Being able to take any given JavaScript file, doing some sort of a some sort of a parsing of that file, creating an AST file, then going over that file and look for the signature, the pattern-based signature that I created for any given packer that I wanted to track, right? In that sense, once I had that proof of concept, then I started to say, okay, so which packer do I want to track? And I had 5 packers that I was able to track. And wanted to make sure that I will be able to have detection for those different 5 packers. So you can see here on screen the 3 first packers that I used, pretty basic ones. The second, the other 2, the 4th and the 5th, are actually a bit more complex in a sense where they are actually what they are doing, giving a payload, doing some sort of a manipulation on that payload. I think when you try to look into JavaScript obfuscation and the repetitive kind of pattern that we see out there, we can see that at the end of the day, it's about taking some payload, which, well, was encrypted in a sense, right? Or obfuscated in many ways, and try to do some manipulation on that given payload to get back with the actual payload that will be executed on that page, the actual JavaScript code that need to be executed. So these are different examples, but represent different packers. But that's the concept that I had in mind. And I created 5 different pattern-based signature for those 5 packers. Now, after we have that capability, we have the proof of concept, we have the signature, the profile kind of signatures or structure-based signature for those packers. Now comes the part when we take that and try to evaluate that on a variety of data sets to try to see results for that. So the first data set that I was using was the phishing data set. It was over 100,000 different phishing pages that I scanned. It wasn't a clean and very accurate data set, but it was big enough and I knew that there are really good samples into that. And the first thing that I was able to see that I have hits on all those 5 different packers that I created signature, a pattern-based signature for those packers. And that's a good sign, right? That means that the technique that I'm trying to use is working. We have detection, right? That's the first part. Second part was to take a much more accurate, much more precise kind of data set, which was malware associated, and try to scan it. And I was also able to see result for that and a much better result. And we'll talk about those rates in a second. The other 2 data sets that I was using were the other side of the planet, right? In that sense, if the first 2 were one that represents something malicious, the last 2 were one that were supposed to represent something that is not malicious, and therefore I used 2 data sets. The first one was the Alexa top 18,000 most popular websites, some sort of a ranking of most popular websites. I checked those websites and I was able to see what a detection that we have there. The second one was a random data set of variety of websites, and I just checked those websites, again, over 16,000 websites in that case. And I was able to see some hits on Alexa and random as well, which is an interesting result, and we'll talk about that. But before doing that, here are some of the detection rate that I had. So the phishing is 2.1, the malware is 26%. That's the interesting number here, right? That means that when I take really precise data set and I examine that data set, what I was able to see is that 26% of that data set representing malware, and some of it was phishing and crypto miners and stuff like that. 26 were using JavaScript obfuscation as a technique to try to evade detection, which is an amazing part. That was a very interesting thing to see. More to that, Alexa and random are 0.5%, which is, well, it's not a high number. It's definitely lower than those that are classified as malicious, but it's still a number that we need to address that. Here are some insights, right? Let's go into that. So JavaScript obfuscation is accurate. That's the first result that I had in mind, that I was able to see. And in that sense, what I'm seeing here is that, first of all, the malicious one, we had hits on them, and that's a good sign. But once I was going into the very specific examples of those that were supposed to be benign, and we saw some hits on them, and I mean the Alexa and random data set, I was able to see that those were accurate as well, because I was able to see that on those websites, what we are seeing actually is that those websites are actually doing some obfuscation for JavaScript. It's not mistake. They were doing that. We'll get into the answers of why they were doing that in a minute. Now, more to that, we were able to see over 4,000 new phishing and malware domains being detected. And let me put some context into that sentence, right? In the context of, we had some techniques that were using hash-based and text-based detection, using the given technique that I'm introducing here, result with better detection, right? I couldn't have those detection on those files because those files were obfuscated, right? They were purposely obfuscated. Someone obfuscated them because they didn't want to have really good detection for those files. And as a result of that technique that I'm introducing here, I have better detection, right? Which is a really good result. Some of those packers were associated with malicious activity only, right? Which is a good, well, indication, because if, for example, we can see the AES decrypt kind of packer functionality, I can say very easily or with a high certainty that once I see detection of AES decrypt being used in the wild, most cases, or in high certainty, that user represents something malicious. It represents phishing, malware, or something on combination of those two, because we don't see hits of those on Alexa and random data sets, right? That's a good sign. That means that I have a detection rate for a malicious JavaScript for, well, not all the packers that I use, but some of those packers. Now, the last item here, and that's where we're starting to talk about the challenges we have for the next part of our presentation for today, is that what we can see here is that obfuscation doesn't equal to malicious, right? Because what we are seeing now today is that on Alexa and random, we also see some of those packers being used, meaning it's not by default that we can see that if a given, packer was detected, that mean on a given website, that mean that that website or that file on that website actually represents something malicious. And that means that our next challenge would be the following. We'll have to answer two questions. The first one would be, okay, so we have some files that are on highly popular or on random website that are being obfuscated. What is the reason for that? Why should someone do obfuscation, JavaScript obfuscation on those websites? We will try to address that question. And the second question, which is much more challenging, would be, okay, so can we introduce a concept, right? We will talk about the concept of doing detection for, let's assume that we already have detection for something that is being obfuscated based on the technique that we talked about just in the last few minutes. But more to that, we will be able to differentiate between something that is obfuscated and it's benign versus something that is obfuscated and it's malicious, right? And that would be a challenge for us, and we'll go through that. So going for the first question, right? Why those files were obfuscated? Those benign and random files that doesn't represent anything malicious were obfuscated. Few answers for that. The first one, email addresses masking. Don't ask me why, but for some reason, many of those websites introduce email addresses to their website. They don't want no one to harvest and scan those websites and utilize those emails and do some bad things about them. So they're doing really, well, simple in a sense, obfuscation for those email addresses appearing on the website, doing security by obscurity in that sense. A different kind of example that we're able to see are cookies, client-side functionality being used. In that sense, it's bad practices. It's not good practices to do some manipulation and creation of cookies on the client side, but some websites are doing that, and they are trying to do, again, security by obscurity and trying to do some obfuscation for that. The third example, which was the most common example for obfuscation being used, was third-party script, sorry. And in that sense, think about it like that. So a given website is consuming some third-party scripts from a third-party application or website, and that script, once being delivered to that website, it's actually being obfuscated. In a sense that those services that gave those scripts are trying to do some obscurity of the nature and the functionality of the code that they are introducing. And what we're able to see, advertisement kind of services, translation services, those kind of services that were doing some sort of an obfuscation for the code, third-party script code that they were adding to their website. And last and definitely least, adult content. Don't ask me why, I didn't get into that, but for some reason a lot of those websites are highly popular, and more to that, some of those websites are actually using obfuscation, and I didn't get into the details of why and how, and let's continue moving forward. Okay, so we talked about the reason of those files being obfuscated, right? The files that were supposed to be benign, and they were benign. Well, now let's talk about how we can take a given file that we know that was obfuscated, and now we need to determine if that file represents something malicious or not. And we'll use two approaches to do that. One approach on the left will focus more on the false positive side, meaning we will look into the websites that are highly popular in that sense and try to figure out if we can do some sort of pivoting and try to do some, let's call it whitelisting of some of those files being used. The second approach will be true positive approach, trying to, well, determine on a given packer and some of the classification that we have, what is the possibility for us to extract some features out of those files and make a decision, a machine learning kind of decision based on that, based on the classification that we have on those files. And we'll go through those two approaches in a second. So first approach, as I mentioned, the false positive one. And in order to better explain what I had in mind, what I was doing the following thing. I took the two data sets that we have, the Alexa and the random, the one that were supposed to be benign, right? Well, they are benign. And what I was doing, I took all those JavaScript files that we saw obfuscation or a given packer, one of the 5 packers that we had, doing obfuscation on those files, and we created a hash value for those files. And then we try to see if that same hash value, well, relevant to many different domains out of those data sets that we were able to see. So the Alexa in the random is the gray circles, the hashes are the orange, and the different domains are the blue circles. So what we are seeing here is actually the same functionality. Let's try to take, for example, the third-party script functionality being introduced to many different domains, right? Being off, like someone took a JavaScript file, obfuscated that file, and use it on many different domains, unrelated whatsoever, because it's a third party doing that for many different websites. And if we go to those files, and we have the same hash for those files, and we can flag those files as not being malicious, as being benign, right? Because we see them consumed by many other websites, then by doing that, we can reduce the problem of having detection of something that might be considered as malicious, because we flag that as non-malicious, right? And doing that technique, we were able to reduce the problem by 20%, meaning we had nearly 240 domains that we were able to see on the random and the Alexa dataset that we were able to see that are using obfuscation, and 48 out of them were actually ones that we can create some sort of a relationship map for them to be able to say, hey, those files are constantly being used by different domains, therefore we can flag them as being benign, therefore we can reduce the problem that we have here. So that was the first approach. The second approach, which is the true positive approach using machine learning, let's try to explain it. That's a concept. We will not get into the really deep dive details of that concept, but we will talk about some of the things that we can do here. So here is an example, the same example that we saw at the beginning of the presentation of a given file being obfuscated, right? And when you look into that file, it's really not readable. It's not like a nice code that you can read, but there are really interesting things about that code that can represent some features. So for example, we have an array, right? And that array had a lot of elements into that. So maybe we can create a feature saying how many elements we see in a given array, or what are the length of those elements in that array, or what are the different characters that are being used on those kind of arrays. And that's a representational feature that now that we have that kind of feature, we can take it into the next level. But before doing that, there are other features as well. For example, what you can see here is you can see that a lot of the functioning and the variables being used here are actually started with _0x. And in that sense, it's a sort of a obfuscation creating variables that are not readable. It's very hard for the human eye to read those variables and try to follow those variables on a given code. So maybe we can count the number of times we can see those kind of variables being used. Or maybe, for example, another kind of feature would be the number of function name and variable name and array names being used in a given file, how many unique of those we can see, and that could also be used as a feature trying to lead us to making better decisions to try to differentiate between something that is malicious versus something that is benign. So here is a graph for that, and that's the experiment here. We took one of the packers that we saw, which is the push shift packer, and we saw the result of that packer, and we tried to differentiate those results for benign versus malicious. And what you can see on screen is that the green one represents something that is malicious, malware, and the blue and the red one represents something that is benign, right? The random and Alexa dataset. But only in a glance on that graph by itself, using only 2 features. We can obviously use more features than that, but trying to create visualization for the experiment. And those features were, on the y, we can see the number of unique identifiers, meaning the number of unique variables or function names or arrays. And on the x's, what you can see is the number of values that we have in a given array, right? Number of elements that you can see. Only using those 2 features, what we can see now on screen is that we have groups that are actually representing different threats on landscape, right? On the upper right, what we can see is a group of some of those malwares, right? We can group them, and therefore they have a unique features or unique set of features that will enable us to make decisions based on that. And the same thing on the upper left side, right? The only problem that we have is in the center of this graph, where we are actually seeing things that are, that some features that are really close to each other, which will create some challenge for us to make decisions based on that. Now, looking even deeper into that, we can also see that the problem is much or less bigger than one would expect, because the area when we see blend of malicious and benign data set is very small. Therefore, we try to take different kind of features and try to build a decision tree based on that, right? And again, this is an approach, this is a concept. It's part of the experiment, it's not the final part of the experiment. And what we were able to see, a very basic decision tree with 3 features. One of them is the number of identifier variables or function names starting with _0x. The other feature was the number of values that we can see in an array. And the third feature was the number of unique identifier, meaning the number of unique variable name, function name, and array names. As 3 features, we were able to build a decision tree that enabled us to do a lot of good detection, right? And here is an example for that, right? We'll take only the right side of that tree, only that right side of the tree by itself. Using those 3 features that I was mentioning, meaning if we have more than 20 identifiers that has a suffix of _0x, and if those samples also have number of values in an array that is greater than 17, adding to that the issue of unique identifier bigger than 92, only using those themselves, we were able to detect 757 out of the 1500 samples that we have for the push shift packer, and classify them as malicious. So that's an example of how decision tree will work. And this is some preliminary result that we have on that research telling us, hey, we have a chance to use some features, and those features will enable us to have better detection and be able to spotlight and track things that are considered as being malicious, right? Now, we had a few questions at the beginning of the research, right? And here are those answers for those questions, or I think that now we need to ask ourselves if we answered those questions. And did we answer the why and how? Yes, we did. What are the numbers behind using in the wild? Yes, we saw those numbers. We saw that JavaScript obfuscation is, heavily being used in in the malware dataset, we were able to see over 25% of those files being obfuscated, which is an amazing number, which means we have to deal with that issue of obfuscation, and we need to make sure that we have really good detection for those. And hopefully we introduce something like that today. JavaScript obfuscation, does it equal to malicious? So definitely no, and we saw example for that, and we explained those examples. Is it possible to detect obfuscated JavaScript? So we definitely answered that question. We saw a technique, an introduced technique, doing a parsing for a JavaScript file representing that file as an AST file, and looking for a structure on that file to try to hunt for obfuscation functionality being used by a given packer, right? Even if that functionality looks a bit different and there is variation of that, the functionality is the same. Now, what are the next steps for me to do in the context of this research? So first of all, I need to release this code, basically the code for the parsing and doing the detection for those different packers. I'm working on that. Hopefully I will do that soon. Add more signature for more packers, right? I choose only 5, the most frequently used, the most common one, but we see more of those introduced on not a daily basis, but we see some shifts and some changes in that area of that packer, and we need to make sure that we're attacking that and we have all the signatures for all those different packers. Refining some of the data set that I was using, for example, the phishing data set was really big, but had a lot of issues with that. And add more features to the machine learning approach that I was using and making much more mature and much more usable. And explore algorithmically the option of being able to track those kind of packer signatures without doing that manually. Because what I was doing was looking into those packers and try to figure out what are the functionality that repeats on itself that do the actual obfuscation of some of that code. What if we would be able to look into that functionality and extract that from different packers automatically? That's the concept behind the scene here. We are at the end of this presentation, and you know the name of the presentation, it's all about the packers, right? With the dashes between the P-A-C-K-E-R-S. And you probably ask yourself, why did I choose that name for the presentation? So the reason for that is because one of those packers that I call the packer contain the following variables in the name of the function, P-A-C-K-E-R, right? And that led me to do that kind of notation or the name for the presentation. But as I was moving forward with my research, I started to see different examples using also packed as the name of the variable. And that was a good sign for me choosing, you know, the structure of a given function and not the actual variables or kind of things that can add to that function. But after doing that, and as I continued to do some of my research, I was also seeing a different kind of representation of the packer variable name with underscore 0x176, whatever, you know, that's also, you know, applicable, right? Regardless of what you put, it's the same functionality, the same signature that I created to that given functionality. Now that led me to think that maybe we need to change the name of the presentation from it's all about the packer to it's all about the underscore 0x1765, etc. It's a joke, hopefully a funny one. Thank you everybody for being here today, and hopefully I was able to contribute some information for you or insights. Would love to hear your questions and get feedback from you. Thank you very much.